What is going on this whiteboard? What are these numbers and what can we do with them? Today on Rithmetic with Ron, we're going to understand scientific notation. Hope you enjoy the video. Let's begin today's discussion of scientific notation by understanding the parts that are involved. So scientific notation has a number at the beginning. It can be a whole number or a decimal, and it's called the coefficient. This number here, this coefficient, can be from 1 all the way up to what we're going to say is less than 10. Okay? If we have the number 10, then we can rewrite that as 1.0 times 10 to a power. So equal to 1 all the way up to just before 10 are numbers for your coefficient. The next part is the base, okay? And the base in scientific notation is always going to be 10, and that's because we count in the base 10 number system. If I count the numbers from 1 to 9, there are 9 numbers. And then if I add 0, I get 10 digits. So from 0 up to 9, there are 10 numbers, and that's called the base 10 number system. The last thing is the exponent. Okay, the exponent tells you how many multiples of 10 there are. And the reason why this is helpful is because scientific notation is going to allow us to write very big or very small numbers in a simple form. So let's go ahead and take a look at a couple examples. We'll start with a couple easy examples, and then we'll get into some very big and very small numbers, okay? The number 500 is in standard form. And if we want to write that in scientific notation, we want our coefficient to be in between 1 and 10. And then times 10 to what power or exponent? Well, what we're going to do is look at the decimal point and say, if I move the decimal point back 2 spaces, one from here to here, and 1 from here to here, that's 2 spaces, okay? And so this is going to be a positive 2. I took the number 500 and I rewrote it with a smaller 5 times 10 to the second power. The 2 comes from the number of places that I moved the decimal. Now, what's interesting is 10 squared is 100. So this is really like saying 5 times 100, since 10 squared is 100. And 5 times 100 equals 500, just like we have, okay? Let's take a look at an example with a small number. What if I have 0.02, okay? Well, my coefficient, again, needs to be a number in between 1 and 10. So since I have a 2 here, I'm going to use a 2, and then I need to go times 10, since we're using base 10, to some exponent. Let's figure out how many places we need for that exponent. 1, 2, this decimal location right here would put the number 2 in between 1 and 10. Since I moved it 2 places, it's a 2, but this time it's a minus 2. Now, why is that? The reason why is because the number that I started with, 0.02, is very small. It's much less than 2. So what I'm really doing is I'm saying this is equal to 2 times 10 to the negative 2 is going to actually be 1 divided by 100. So 2 times 1 over 100 equals 2 100ths or 200ths. But the decimal, 0.02, can be read as 200ths as well. So what we see from this is that you have a coefficient, you have a base, and you have an exponent. And from your original number, if you move the decimal to the right, then there's a negative exponent. If you move the decimal to the left, it's a positive exponent. The number itself is always the number of spaces that you move the decimal, okay? But as far as the exponent itself, if you move the decimal to the right, then the exponent is negative. If you move the decimal to the left, then the exponent is going to be positive, okay? Let's take a look at a couple more examples of much bigger and much smaller numbers. All right, let's see something about our planet Earth. If I look up online, I see that Earth has a mass, or in this case we'll call it a weight, of 5.972 times 10 to the 24th kilograms, okay? Because this is a positive number, this is actually a very big number, okay? And let's see what happens if I were to write this out in standard number form. This is the number of kilograms that the Earth is estimated to weigh. That's just an absolutely huge number. Now, let's check and see. This coefficient is in between 1 and 10, so that's correct. And our exponent is positive because to go from the scientific notation to the standard form, we moved the decimal from the original number. We would have to move it this way to the left to get our coefficient, okay? So let's count. If we start from here, we get 1, 2, 23, 24. So from the original number, 24 place values to the left is why I have an exponent of 24. Now, all that work just to say, if you had to do adding, subtracting, multiplying, or dividing with a number this size, that would be very tedious. And so scientific notation is very helpful as a way to quickly write a very large number. Let's take a look at another example, but with a small number. And again, looking this up online, what I find is that the average diameter of an atom is about 2.5 times 10 to the minus 10 meters, m for meters, okay? Now, the fact that this exponent is negative tells me that the real number is very, very small, okay? So what would this actual number look like? 10 spaces from 0.0 gets us to 2.5, okay? That means that if you were to write the average diameter of an atom in meters, you would have this number, this many zeros before you wrote the digits. And again, just like the very big number, a small number like this takes up a lot of paper and takes a lot of thinking if you're going to do arithmetic or multiplication or any other math operations on a number this small. This would be very difficult. Imagine trying to add or multiply, not add, but multiply these two numbers in these forms. What a ton of work. And think that when this was invented, mathematicians didn't have calculators or computers. This was all done by hand. So now that we have seen that scientific notation is useful for writing very big numbers in a simple form or writing very small numbers in a simple form, now we're going to go and see how do I add, subtract, multiply, and divide with this method. The first example that we're going to do is we're going to add. And what if I say 5.1 times 10 to the second, and I'm going to add 3.2 times 10 to the second, okay? When you add, and it's true for subtraction as well, when you add numbers in scientific notation, the coefficients have to be the same, okay? And there's ways to make them the same if you're given two numbers where they're different, and I'll show you how to do that next. But right now, for this example, the exponents are the same, and so I'm going to add the coefficients. 1 plus 2 is 3, I have a decimal point, 5 plus 3 is 8, and I'm going to keep times 10 to the second power, okay? And the way that you can check this, remember, is since we have a positive exponent, then we can take this scientific coefficient and we can move the decimal point 2 places to the right to change it into the standard form, and we would get 510. And here, 3.2 times 10 to the second, well, let's move this decimal 2 places to the right, and we get 320. If I add those numbers, 0, 3, and 5 plus 3 is 8, look at 8.3, if I move the decimal 2 places to the right, 1, 2, I get 830. okay? Let's do one more example, but this time let's say 5.1 times 10 to the second, and this time I'm going to say 3.2 times 10 to the third, okay? What we have to recognize is that because we have 10 to the third, this number is actually much bigger. And so I cannot add these the way they are right now. What I need to do is rewrite this number so that it has an exponent of 2, okay? So let's step over here and see what that would look like. To make this an exponent of 2, that's making this number smaller. To offset that, I have to make the coefficient bigger, all right? So that means that this is going to be 32 times 10 to the second power. Now I'm going to rewrite this, and actually I think what I'll just do is rewrite it over here. 5.1 times 10 to the second plus 32, not 3.2, but 32 times 10 to the second. So by decreasing this exponent, I have to make the coefficient 10 times bigger, since the exponent is now 1 unit smaller, which would be 10 times smaller. Now they have the same number, and I can add 5.1 plus 32 is going to be 37.1 times 10 to the second. But remember that to write it in the proper form for scientific notation, that first coefficient needs to be in between 1 and 10. It can be equal to 1 all the way up to smaller than 10. So to get this number 37.1 into a number between 1 and 10, I'm going to move this decimal back 1 space, which means since I made the coefficient 10 times smaller, I have to make the exponent, or the base, 10 times bigger, which means increasing this by 1. So to do that, my answer is going to be 3.71 times 10 to the third. And one thing I would say is, as you're practicing these, don't be afraid to check your answer with a calculator. We do have tools that we can use. We just want to learn how it's done by hand, and then we can use the tool to do the problems quickly. Let's try a real quick example with subtracting. Similar to adding, what we need is we need to make sure that our exponents are the same. So 3.1 times 10 to the fourth, and I'm going to subtract 1.1 times 10 to the fourth, okay? And just like when we were adding, if these exponents are not the same, then we need to rewrite the coefficient so that the exponents match, and then we can add or subtract the coefficients and keep the answer the same in terms of exponents. So here, because these are the same, I already know that the answer is going to be times 10 to the fourth. But now I can look at the coefficients and say 3.1 minus 1.1 is just 2, okay? I'm not going to do an example here of different exponents because the process would be the same as the previous example with adding. Let's go on and do multiplication and division. All right, to multiply scientific notation numbers, what we're going to do is something a little bit different. Let's do a simple example here. 2.0 times 10 to the third, and let's do times 3.0 times 10 to the second, okay? If I want to multiply two numbers that are written in scientific notation, I'm going to multiply the coefficients, very similar to how we added or subtracted. 2 times 3 is 6, okay? Now, what I'm going to do different, though, is with multiplication, I need to add these exponents. So 3 plus 2 is 5. And real quick, this is a much bigger number, but let's see why that happens. 2 times 10 to the third, well, I can write 2, and then if I move the decimal 1, 2, 3, I would get 2,000. 3.0 times 10 squared would be 3, and then I move this decimal 1, 2, and I would get 300. If I multiply those two numbers together, recall that when you multiply numbers that end in 0, you can multiply the numbers at the beginning. 2 times 3 is 6, and then look at how many zeros I have, okay? I had 3 zeros here, 3, 3. I had an exponent of 2 here, 2 zeros. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 6 times 10 to the 5th is 600,000. Okay, let's do one more example quick with division. We're going to divide, okay, and this is very similar to multiply, just a little bit different. Let's try 9.0 times 10 to the 7th, and we are going to divide by, I'm going to write it like this as a fraction. You can use the little division symbol like this if you want to. I'm going to write this as a fraction just because scientific notation is a little bit longer. Let's go ahead and say 3.0 times 10 to the 3rd power, okay? I picked easy numbers here just so that you can see, but it would work even with more difficult numbers. Let's take and divide the coefficients. 9 divided by 3, well, that is, let's write the answer over here. That's going to be 3. 9.0 divide by 3.0, okay? Divide the coefficients, and you get 3. But instead of adding like we did before, we're going to subtract. We're going to take the top exponent, and we're going to subtract the one underneath, okay? Let's try that out. 7 minus 3, so this is going to be times 10 to the 7 minus 3 is 4, okay? 7 minus 3 is 4, so 3 times 10 to the 4th. Let's do one more example because I want to show you that with division, if you have a bigger number in the denominator, you actually will end up with a negative exponent. How about 7.5 times 10 to the 2nd? And we're going to divide that by 1.5 times 10 to the 4th. And at the end of this, I'll show you what these numbers really look like so that you can check it yourself with a calculator and see that it does work. We're going to begin by dividing the coefficients. 7.5 divided by 1.5 is actually a whole number 5. And then we're going to subtract, okay? But we're going to start with the top and subtract the bottom. So we're going to go times 10 to the 2 minus 4. If I start with a positive 2 and I take away 4, I'm going to end up at negative 2. Okay? Now let's see what kind of a number this really is and what kind of numbers these are. 7.5 times 10 to the 2nd is really 7,500. Nope, I did that wrong. It's 750. Why? Because from 7.5, if I go 1, 2, 1, 2. So 750, and I'm going to divide by 1.5 times 10 to the 4th. Well, if I have the decimal here, and I go 1, 2, 3, 4, 1, 2, 3, 4. That's correct. Okay. That means that I'm going to have 750 divided by 15,000. If I put that into a calculator, I get 0.05. Now let's see what this number really looks like. Remember that if we had times 10 to the negative 2, we could rewrite that 5 times, let's see, 10 to the 2, 10 to the positive 2 would be 100. So because that's a negative 2, it's going to be 1 over 100. So instead of 100 in the numerator and making it 100 times bigger, we've got 100 in the denominator. Now, if you multiply this, you get 5 in the numerator and 100 in the denominator. 5 hundredths, and this decimal can be read as 5 hundredths. So today we saw how scientific notation is actually a really useful tool for writing big numbers or small numbers in a form that's easy to deal with. While we have calculators and computers nowadays, it's important to understand where this math came from, and we saw how useful it is for adding, subtracting, multiplying, and dividing. Hope you enjoyed the video. Go ahead and leave me any comments, hit subscribe, and we'll see you next time.